Well, all right. Let us begin our last topic in this class, and that is about continued fractions. The topic is actually big, and I'm not in a position to tell you everything one knows about the subject. I will give an overview, mostly telling you what kind of theorems are there. I will prove some theorems to give you a feeling of what kind of argument, what sort of arguments are involved into discussion of continued fractions. Possibly I will show you some application of these techniques. Let me start with a very vague description what a continued fraction is. In general, in mathematics, they say that any expression like that, a0 plus 1 divided by a1 plus 1 divided by a2 plus and so further, is a continued fraction. This is a pretty vague definition. The dots tell us that there may be quite a few of them, maybe infinitely many, maybe finitely many, in fact. And in principle, this is can be anything. The expression, especially if it is infinite, may make sense or make little sense. We restrict that general vague definition to a very narrow one. So for us, for the purposes of our discussion, a0 is an integer a0 may be positive or negative, and all ai's with I starting from 1 and further are positive integers. We still, it is not at all obvious that this expression under this restriction makes sense if there are infinitely many of them. First of all, writing continued fractions this way is very inconvenient. So we will start with a more convenient notation, writing our expressions not as a ladder but in a row. So notation instead of writing this, we write it this way. A0 semicolon A1 A2 AN, we write for finite continued fraction expression, which means A0 plus 1 over A1 plus 1 over A2 plus and so forth until the last one plus 1 over AN and it stops. And we write simply without the last one, a not semicolon, a1, a2 dots for an infinite expression. It is not obvious at all that the infinite expression makes sense. The finite expression definitely does. A point is that we always have to calculate it backwards, starting from here. So what is, this is example from the text. How do we calculate it? So that to make it clear, what does this letter mean? What does this notation mean? Let me calculate this thing, -2, semicolon, 1, 3, 5. What is that? That is, by this notation, this is this letter, starting with -2 plus 1 over 1 plus, this is this one, 1 over 3 plus, this is the 3, 1 over 5. Now it is clear what it is. We will calculate. This is equal to, I will continue the example, -2 plus 1 over 1 plus, all right, 3 plus a fifth is 16 over 5. This is 3 plus, and 3 plus a fifth, and 1 over flips it, so this is 5 over 16. 1 plus 5 over 16 is 21 over 16, and 1 over flips it. So we have -2 plus 16 over 21. Now we calculate that this is equal to -26 over 21. So this is how we understand this expression. We always calculate it from right to left, from downstairs back upstairs. And of course, we cannot do that for an infinite expression because there is no and downstairs to start with. In fact, one of our goals here is to make sense out of infinite expressions as well. These are going to be, as you probably expect, certain limits, taken in the right direction from left to right. Let me introduce yet another notation for the remainder. If it's legit desire to cut it somewhere, to cut this somewhere, let us introduce notation for that kind of truncation. Rk is going to be the kth remainder. And for the kth remainder of, let me write it here. The kth remainder of the thing, our expression A naught A1, A2, no matter finite or infinite, in both cases, it is going to be defined as our key is equal to A keys, semicolon, A key plus 1, A key plus 2, and so further till the end here, if there is an end. We assume that this key does not exceed n if we have the last n, if so for the thing A naught, A1, A2 up to AN. Of course, then it makes no sense to cut after the last term, so the remainders are only finitely many of that. There are only finitely many remainders if the whole expression was finite. So I want to stress we write semicolon in the first place, and the first is just an integer. It may be negative, as this example shows. All others are going to be positive. There is a drop of symmetry here. And of course, if we forget about our running assumption that all of them are positive integers, we can write something as the whole fraction A naught plus 1 over A1 plus 1 over A2 plus, and so further, is equal to A naught plus 1 over A1 plus 1 over A2 plus and that finishes with our key. I'll put quotation signs because this thing, so this is true, at least for finite continued fractions. At the same time, I put quotation sign because this one actually does not fit our definition. We wanted all of them to be positive integers. The remainder is positive, but most probably is not an integer. So this is not really a continued fraction in the frames of our definition, while this is. So the equality is shaky as a number. They are, of course, the same. This is how we define remainder. So we somehow calculated back from up to key and called all that our key. After that, we continue calculating as usual when we evaluate this expression. So we evaluate it from the last, if there is a last, till here, and stop, and all this is a remainder. After that, the calculation may be continued if we want to evaluate the expression. Can be continued with the remainder instead of the tail here. That's the notion of kth remainder, mostly notation for kth remainder. Let's look again at this example here. We see that, and that is not a surprise at all, that a finite continued fraction can be calculated, at least in this case, and actually it is clear that in every case, a finite continued fraction, finite expression like that, can be calculated, and what we produce is a rational number. Of course, we produce a rational when we use nothing but flipping fractions and adding fractions. After all, we end up with a rational number because a naught has a sign. It may be positive or negative. We may get positive or negative number at the very end. This one, without a naught, is strictly positive because we deal with all positive numbers. All signs are pluses. So we flip fractions, add fractions, flip fractions, add fractions. We never, as here, add fraction, flip fraction, add, flip. We never produce a negative number until the very end. Clearly, what we produce is a rational number. The natural question is, do we produce any rational number in this case, in this way? And the answer is yes. That is proposition 1 in the text and here, that any rational number can be written as a finite continued fraction. How do we prove that? We make a construction. So the proof presents an algorithm. It shows a way to achieve the goal. So the proof is constructive. Constructive means shows a way to achieve the goal. The goal in this case is to produce a continued fraction out of a rational number. So we start with a rational number alpha in Q. So let alpha be a rational number. The first step is kind of obvious with 1. So what we want this kind of expression, or in our notations, this kind of expression, for a rational number. This kind, finite 1 for a rational number. Who is this term, a0? It's an integer, positive or negative. If it took only positives, then we'll not be able to present negative numbers because all positive. Therefore, it has to have a sign. But what is that? This is an integer which should be pretty close to our rational number. The thing is positive and smaller than 1. We will see that. Thus, this is integer part of our rational number. So the a0 of our presumed continued fraction should be the integer part of our rational number. So we'll set a0 to be integer part of alpha. Here is a comment about notations. Very common notation. Not only in number theory, but in mathematics in general, for not necessarily rational, just real number alpha, this, or frequently they write it this way with not brackets but half brackets, is the greatest integer not exceeding alpha. So this means that integer part of an integer is this integer itself, and integer part of 1.3 is 1, and a very general misconception. What is natural part of negative 2.9? Negative 3 is closer, but it should be the greatest integer not exceeding. The greatest integer not exceeding is not 3, although 3 is closer. It is not rounding. Or, if you want, it's rounding down. Always down. Rounding to the integer down. It's negative 2. It's not the closest, but rounding down always. In particular, we always have that so negative 3 down. Sorry. And negative 2.1 is also negative 3, always down. Sorry, I said correctly and calculated wrongly. Always down. So in particular, we always have that alpha minus integer part of alpha positive. Alpha is always bigger way, round down. At the same time, it never exceeds 1. So, now we set A naught to be integer part of alpha. And now let us write delta as alpha minus A naught. According to this inequality, by the way, may it happen that they are equal? Yes. May it happen that this is 1? No. This inequality is non-strict, this one is strict. You cannot round 3 down to 2, integer part of 3 is 3. But, exactly because integer part of 3 is 3, it may be equal to 0. So that difference may be 0 if that difference is equal to 0 exactly when alpha is an integer. So we set delta to be this difference, and according to this inequality, we have that delta is between 0 and 1 just because of this inequality. We are done if delta is 0. In this case, that means alpha was an integer, and we already have this expression, which doesn't have all a's and have a naught only. If delta is not 0, then it is positive, and we can flip it. So, assuming delta is not 0, we are not done. We set R1 to be 1 over delta. This is going to be the first remainder. Indeed, we have alpha is A0 plus what? Delta. Of course, alpha is A0 plus delta. And this is same thing as A0 plus one over R1. That's the first remainder. All right. Now we set A1 to be integral part of R1. Delta was smaller than 1, so R1 is strictly bigger than 1 because delta is smaller than 1. 1 over delta is bigger than 1. So integer part of an integer bigger than 1 is a positive integer. Again, we introduce the same game. Now our next delta is R1 minus A1. And again, A1 is integral part of R1, so again we have that delta is smaller than 1, and this is this inequality, difference between that number and its integral part, smaller than 1, non-negative. And again, if delta is 0, that may happen, we're done. If delta is not 0, we introduce now R2 to be 1 over delta, and again, this is bigger than 1, because delta is strictly smaller than 1. So flipped is strictly bigger than 1. This is our second remainder. Indeed, alpha is A naught plus 1 over R1, but R1 is A1 plus delta. This new delta. And this is same thing as A0 plus 1 over A1 plus 1 over second remainder R2. And now it becomes more or less clear what do we do next. Of course, next we continue, we set A2 to be the integral part of our R2, and this is again a positive integer because R2 was strictly bigger than 1. We again introduce a new delta, which is the difference, and that is again by the same token between 1 and 0. And again, if delta is 0, we're done. Why that? Because what does it mean that delta is 0? The difference between R2 and and its integral part is 0, means R2 is integer, a positive integer. So this was a positive integer. This is our expression A naught semicolon A1 comma A2. We're done. Again, if delta is not 0, then we do R3, which is again 1 over delta, and this is again bigger than 1 because delta was smaller than 1. And that is our next remainder. Now we can write our alpha is A naught plus 1 over A1 plus 1 over plus 1 over R2, and for R2 we write A2 plus delta, A2 plus, and delta is 1 over R3. So R3 is the next third remainder. And what we see at every step, we calculate next remainder and start to expand it further into a continued fraction. Take the integral part of our next remainder. That is a description of algorithm, a procedure. That's not yet a proof of our proposition. So what do we need to prove? The proposition claims that any rational number can be written as a finite continued fraction. So we want to prove that this procedure stops at a moment. So to prove that algorithm stops after finitely many steps. Let us try to do that. So, by construction, at every step, our remainder is a positive rational number. It's irrational every time because we deal with nothing but integers, so delta is the difference between the previous remainder, which was a positive rational number, and its integral part, an integer. We flip, so this is a positive rational number, smaller than 1. We flip a rational number, we get again a rational number. So all remainders are positive rationals. I'll assume, so note that all remainders are key constructed by the algorithm are positive rational numbers. So we make now a generic step. So let R key be LB with integers. Positive integers. And B. And we assume that this fraction is written in lowest terms. So that otherwise A and B are not defined. They are defined up to a common multiple. Greatest common divisor of A and B is 1. The fraction is written in lowest terms. What do we do on every step? We set our next member of continued fraction to be the integral part of remainder. So we set a k to be the integral part of r k. After that, what do we write? We write delta, which is r k minus, a k. And I can write that this is a over b, which is r k minus a k, which is a minus b a k divided by b. And I want to write it c over b with positive integer c, a minus b a k. What I want to say about these integers, it is important to note that c is smaller than b, because our delta, the difference between remainder and its integral part, is always smaller than 1. Delta smaller than 1 translates to this positive integer. There, both b was positive and delta is positive, so c is positive. And delta, which was always smaller than 1, this difference is smaller than 1 because a is integral part of r. So delta is smaller than 1 because r because delta is smaller than 1. Delta, which is r k minus k integral part, is so we've got this important and simple inequality. Let us continue our procedure according to the algorithm just described. What we do, we flip delta. Flipping delta, we have, if delta was 0, that means c is 0, and it stopped at this step. So we want to prove what we are proving, that the algorithm stops. C is 0, the process stops. delta is 0. C is not 0. Delta is not 0. We can flip it and produce the next remainder, r q plus 1. And we prove that it stops. If C is 0, we don't have anything to prove. The process stopped. C is not 0, the process continues. 1 over delta, which is B over C. Now, our important observation can be interpreted the denominator of the next remainder, r q plus 1, as smaller than the denominator of RQ. Remember, we wrote this in reduced term, in lowest terms. So the greatest common divisor of A and B is 1. This may be not in reduced terms, but that does not change this conclusion, because if I can reduce this fraction, still C stays smaller than B. So still the new denominator, it becomes even smaller and smaller than this B, not this one, not reduced. Although this one, it's also true, but what is important, the C, the denominator of the next remainder after reduction, even before reduction, and therefore even more so after reduction, is smaller than the denominator of the previous remainder. So the first remainder, R1, has some positive integer as a denominator. It is some rational number bigger than 1, whatever. So we can write this rational number R1 as a reduced fraction. So let me write it. The first remainder R1 has a positive integer as its denominator. After that, every next one has a smaller, they are all positive integers, smaller by at least 1, strictly smaller. All inequalities were strict. Smaller positive integer every time smaller and smaller. Thus we can conclude the process has to stop. Thus They are all positive integers, become smaller and smaller at every step. The process has to stop. That happens when the denominator of a remainder Rn becomes 1 if that denominator is 1 in remainder is integer, then immediately our integer part is the same, and delta is the difference between remainder and its integral part, which is 0. Delta is 0, the process stops. That's it. We proved that at some step the process stops. This, the proof is finished. As a remark, the same procedure can be done. This algorithm works independently whether alpha is rational or not. Just if it was not rational, the process will not stop. It will continue to produce A's. For rationals, a proposition provides a map. Provides with a map. From rationals to finite continued fractions. On the other hand, we know how to evaluate a finite continued fraction. This expression can be evaluated to produce, just calculating from right down to left up, as in the example, to produce a rational number. So clearly there is an inverse map. Inverse map. Which is evaluation of a finite continued fraction expression. It is tempting to conclude we have a one-to-one correspondence. Not exactly. there is an obstacle. This is not exactly a one-to-one correspondence. Here is the reason. The number a half can be evaluated out of two different expressions, 0 semicolon 2 and same thing, 0 semicolon 1 1. Our algorithm, which I've described here this way, out of a half will produce this one, not this one. And more generally, for any continued fraction produced by the algorithm, finite continued fraction produced by the algorithm from proposition 1 always satisfy. So this, if it produced a fraction a0, a1 up to an, always satisfies but the last one, this an, is bigger than 1. This is easy to obtain from analysis of what we are doing there. I'll leave it as an exercise for you. You can easily figure out why that happens. And it's going to be just a little bit more difficult that is formulated as first exercise in the text to prove that this is the only glitch. Namely, exercise 1 in the text. The correspondence between rationals and the set of continued fractions sorry, A0. A1, AN, with AN bigger than 1. They are all positive integers, just the last one should not be 1. A0 is allowed to be an integer, not necessarily positive. So this correspondence is 1 to 1. So this arrow means doing the algorithm, which is finite, and producing a continued fraction out of a rational number. This arrow means calculating a rational number out of a continued fraction, evaluating the continued fraction. What we need to prove, we have two inverse maps which give us identity. The only thing we need to prove now, the only thing we need that something like that, after we impose an extra condition, does not happen.